Let's look at some prototypical examples of subspaces. So if we're looking at Fn, then we could look at the subspace, which consists of, say, let's work in F3. And so we'll look at triples then that all have the same value b in the third coordinate. Okay, so all points from F3 that have a b in the third coordinate. All right. And so b is just going to be some fixed number. Some fixed scalar. Okay. So let's see. So let's check the addition property. Is it closed under addition? Well, let's see. So is it the case that if we look at x1, x2, b, and some other point from u, let's say y1, y2, b, and we add them together, do we get something that's back in u? Well, we look at the way that the operation is defined. Oops. And we have x1 plus y1 in the first coordinate, x2 plus y2 in the second coordinate, and b plus b, commonly known as 2b, in the third coordinate. So is the sum back in u? That's the question that you need to ask. And so the answer is, well, in order to be in u, you need to have this condition right here, that you have a b in the third coordinate. So the question is this equal to b? And the answer to that question is that b equals 2b if and only if b is equal to 0, which you can see by subtracting b from each side of that equation, right? Okay. So if we have, and then I'll let you check containment of 0 and scalar multiplication. But it turns out that u satisfies both of those as long as b is equal to 0. And we can generalize this idea very greatly. Well, let's put that over there. Okay, so suppose we've got a collection of points actually, let's call this n. Okay, so we've got all the, whoops, wrong, there we go, points in Fn such that these points, I can get rid of maybe that one, satisfy a given homogeneous, and because we just found out in the previous example that it only works if it's homogeneous, linear equation. And in fact, we can replace equation with system of equations. Okay, so now this is what we had in the previous case. So the homogeneous linear system in general for this example is the one that looks like x3 equals 0. So it's a system consisting of one equation, but that is a linear equation, and it is homogeneous because it's set equal to 0. So it's a little bit trivial looking, but it works. So my point is just that this one that I'm writing down is a generalization of the one that we saw in the previous step. And so for short, I could just say, okay, those are the points of Fn that satisfy ax equals 0, where now we're doing matrix multiplication, and a is going to be some fixed m by n matrix that allows us to encode our system of equations. Okay, so then the key points that we have here is that the homogeneous part means that the subspace passes through 0, so that it contains 0. And so that means that the equations have to all be set equal to 0. You can't have a non-zero constant on the other side. And the fact that these are linear equations, this means that the resulting shape of a vector space is that it has to be flat. It's not going to be curved. And so, as a consequence, we then see that subspaces, well, it's going to look like 0, the 0 space, or it's going to be a line, or it's going to be a plane, or some higher dimensional version of a plane, which we call, a hyperplane. And the k there is to represent the number of dimensions or free parameters in that hyperplane. Passing through the origin. And that's actually if and only if it's a subspace. So now we know what all the subspaces of Fn look like. They look like these planes and hyperplanes and stuff like that. What about if we look at Fs? So let's say that S is some interval in the real line. Doesn't have to be, but I'm going to talk about limits and derivatives, and I know that you're familiar with those for intervals in R. You might be less familiar with what that means if we're talking about complex valued functions. So we'll just stick with real valued for now. The functions defined on R. And we'll take C to be a point of S. So then each of the following subsets of Fs, so functions from the interval AB into R, is a subspace. Okay, so I could say, let's take the collection of functions such that they vanish at C. Okay, so all the functions that are equal to 0 at C, that forms a subspace. If I were to take all of the functions whose limit as x tends to C is 0. So that's all the functions that tend to 0 at C. They might not actually be equal to C there or whatever. Or if I look at derivatives, U prime, sorry. The whole point is that that's supposed to be a derivative. So if I look at the derivatives there, the collection of functions whose derivative is equal to 0 at C, that also is a vector space. And so these here we're looking at applying evaluation to a function. Here we're looking at applying limits to a function. Here we're looking at applying derivatives to a function. And the key point, the sort of general thing that makes all this work, is that these are all linear operations that you can do to a function. Right, so you know that the limit of a sum is equal to the sum of the limits when the limits are defined. And you know that the derivative of a sum is the sum of the derivatives. It's like one of the first things you learn about derivatives. And you also know that things work out for scalar multiples in both of those cases. So that's what I mean by saying that those are linear operations that you can do to functions. But there's also many more. So we'll see, so things like the periodic functions. So say you take like all the functions with a given fixed period, 2-pi periodic functions, those will form a vector space. If you look at the even functions or the odd functions, those will form vector spaces. There's all sorts of different things. And you can also generalize the point C that I had for these examples. So instead of just saying functions which are 0 or have derivative 0 or limit 0 on this set, you could change that instead to, functions which are vanishing, on some, say, little epsilon disk around C, or some other set that you might like, as long as limits and derivatives are defined on it.